Thank you. John, did you want to unmute?
That's probably a good idea. Good afternoon. This is John Sullivan again, KG7WFQ with this afternoon's class. And today we are going to, I guess I have to acknowledge that or it won't let me advance. Okay, there we go. Yep. So we're going to be covering a number of electrical principles, a lot of terminology and units, conversion of electrical units, current and voltage. These are all the subtopics: conductors and insulators, series and parallel circuits, alternating and direct current, capacitance and inductance terminology again, and units. Going to talk a lot about Ohm's law and decibels and calculating power, and some radio frequencies definitions and units, and impedance definition and units. So a number of new kinds of terminology or things that may be new to many of you. So just heads up on that. And speaking of strange terminology.
Here at Rockwell Automation's World Headquarters, research has been proceeding to develop a line of automation products that establishes new standards for quality, technological leadership, and operating excellence. With customer success as our primary focus, work has been proceeding on the crudely conceived idea of an instrument that would not only provide inverse reactive current for use in unilateral phase detractors, but would also be capable of automatically synchronizing cardinal gram meters. Such an instrument, comprised of Dodge gears and bearings, Reliant electric motors, Allen Bradley controls, and all monitored by Rockwell software, is Rockwell Automation's Retroencabulator. Now basically, the only new principle involved is that instead of power being generated by the relative motion of conductors and fluxes, it's produced by the modial interaction of magnetoreluctance and capacitive diractance. The original machine had a base plate of prefamulated amulite surmounted by a malleable logarithmic casing in such a way that the two spurving bearings were in a direct line with a panametric fan. The lineup consisted simply of 6 hydrocoptic Marsal vanes, so fitted to the ambifacient lunar wane shaft that side fumbling was effectively prevented. The main winding was of the normal Lotus O deltoid type placed in panendermic semi-boloid slots of the stator. Every 7th conductor being connected by a non-reversible Tremie pipe to the differential girdle spring on the up end of the gram meters. Moreover, whenever fluorescent score motion is required, it may also be employed in conjunction with a drawn reciprocation dingle arm to reduce sinusoidal depleneration. The retroencabulator has now reached a high level of development, and it's being successfully used in the operation of Milford trunnions. It's available soon wherever Rockwell Automation products are sold.
So hopefully you won't think that the terminology we're going to cover is as much gibberish as that is, but let's take a look. Some terms we want to talk about is power. Power is the rate at which energy is consumed, and power is measured in watts, is a unit of measurement for power. Resistance, as it implies, is the opposition to electric current, and it's measured in ohms. Voltage is a measurement of electric potential, potential energy, or electromotive force, and it's measured in volts. Current is the flow of electrons, and it's measured in amperes, or usually amps for short. Frequency is the number of cycles per second a wave makes, and it's measured in hertz. Now, some of these terms you've already seen, but if some further acronyms and definitions: AC alternating current, A is the abbreviation for amperes, also amp for amperes, either one. Little d, capital B for decibel. DC direct current, E for electromotive force. Also EMF is also electromotive force. Capital H, little z, hertz for frequency measurement. I for current. Then we have kilohertz and megahertz. So we already had hertz, so 1,000 hertz or kilohertz is kHz, and 1,000,000 hertz or megahertz is MHz. Notice that the K is a lowercase k and the M is a capital M in these abbreviations. So there is a difference between them. P for power, R for resistance, RF for radio frequency, V for volt, and the Greek letter omega is used to symbolize ohm, which is our measure of resistance. Here, just quickly in a chart form, you can see we have power is watts, resistance is ohms, voltage is volts, current is amperes, frequency is hertz. You'll be seeing quite a bit of that. Now, when we take a look at the numbers themselves for these measurements, you can see how everything's in powers of 10. So if we're talking about things larger than 1, for instance, hertz on the left, we've got 1 hertz. A kilohertz would be 1,000 hertz. Megahertz is 1,000,000 hertz, and a gigahertz would be 1,000,000,000 hertz. For things smaller than 1, it's going to be 10 to a minus power. So it's going to be, for example, on the right, 1 ampere, or then 1 milliampere has 2 zeros after the decimal point before you get to the 1. And for each of these different levels, you're adding 3 zeros. So microampere is 5 zeros in front of the 1, and nanoampere is 8 zeros in front of the 1. So those are the terms we need. You'll see commonly kilo, mega, giga, milli, micro, nano, and sometimes pico, which is adds another 3 zeros to it, trillionths. Okay, so I'm going to be going through the questions in different order than they're listed in the question pool. I've tried to group them more by subject so that the more closely related questions are at the same time here. So if you're trying to follow along through the FCC's question pool, it will not be in that order. We will cover every question, but it's in a slightly different order. So our first one we want to look at here is, what is the name for the flow of electrons in an electric current? And I just mentioned that when we talk about electric circuit, what we talk about is current is the flow. Okay. An electrical current is measured in which of the following units? That would be amps or amperes or amps. That's current flow. What is the electrical term for the force that causes electron flow? The force or electromotive force, that would be voltage. Voltage is the force that causes electrons to flow. What are the units of electrical resistance? Okay. Well, that's going to be ohms, the Greek letter omega, ohms. Which term describes the rate at which electrical energy is used? Remember, that was the first definition I talked about, power being the rate at which electrical energy is used. The answer is power, C. And electrical power is measured in which of the following units? This one's has a little bit of a tricky thing thrown in there. It's watts, not watt hours, but watts for power. And what is the unit of frequency? And that is hertz, cycles per second or hertz. Okay. So now we get into the math part, and you'll find there's a number of questions in this pool that deal with the expression of these decimal differences. So how many milliamperes is 1.5 amperes? Well, we know that a milliampere is 1,000. So 1.5 thousands would be what? Would be 1,500 milliamperes, because milli is for 1,000. So 1.5 amps is 1,500 milliamps, which is equal to 1,500,000 hertz. Okay, so we know that a million would be a megahertz, but that would be 1.5 megahertz. The equivalent of that would be 1,500 kilohertz. Okay. Which is equal to 1 kilovolt. So remember, kilo is 1,000, and kilo and mega and giga for things greater than 1. So it wouldn't be 1/1000th, and it's not 100. And we know that it's 1,000 volts, so it's answer C. It's not a million, it's 1,000. Megavolt would be 1,000,000 volts. Kilovolts, 1,000 volts. Answer C. Which is equal to 1 microvolt. Okay, so micro is again millionths, so it's 1/1,000,000th of a volt. So 0.000001. Which is equal to 500 milliwatts. Well, we know that 1,000 milliwatts is a watt, so 500 would be a half of a watt, 0.5 watts. Answer B. Which is equal to 3,000 milliamperes. Okay, so once again, we know that a milli is 1,000, so 3,000 milliamps would be 3 amps. Okay. Which is equal to 3.525 megahertz. So essentially here, how do you convert megahertz to kilohertz? And basically you move the decimal point to the right 3 places. So you end up with 3525 kilohertz is the equivalent of 3.525 megahertz. Answer C. Which is equal to 1,000,000 picofarads. So remember, it went milli, micro, pico, nano. So, and these are by factors of 1,000. So, oops, did I hit it right? I did. So that would be 1 microfarad. 1 microfarad. Because 3 decimal points for nano, 3 more to get to micro. So 1 microfarad. Which is equal to 28,400 kilohertz. Well, we're not, obviously answer A has to be wrong because that's also in kilohertz. So the question is, what is 28,400 kilohertz in megahertz? And again, 3 decimal places, 28.4 megahertz. Which is equal to 2425 megahertz. So this time we're shifting to gigahertz. So it's going to be 2.425 gigahertz. Again, move the decimal 3 places. Okay. Any questions on that? It's really kind of just memorizing how many decimal points you have in each of these to get the equivalents. But you will see at least one question on that on the exam. Okay, so the next bunch of subtopics we want to talk about is the list here, several different things, and we're going to start off with talking about voltage, current, and resistance. In order for electricity to flow, you have to have a completed circuit. You have to have a path through which the electrons can flow, a complete path of some sort. So in this example here, you can see on the left, there's a battery here, and it's producing current, which is going to flow. It's going to split off into 2 directions here. It's going to go through this current meter, this amp meter, through a resistance load. It's also going to go this way through this branch, through this voltmeter, and it's all going to come back to the battery. Those are complete circuits. Voltage, you can see we have a meter here. It's always measured in parallel across a load. So here's a load, you measure the voltage across it. Whereas current is measured in series. So we want the current to flow through the meter, all the current that you want to measure to flow through that meter and nothing else. So voltage is measured in parallel and current is measured in series, and we'll see that again in a little bit. So let's take a look at an example of a circuit. As I said before, for current to flow, there has to be a complete path from the source back to the other side of the source. So here's an example of a battery connected to a switch and a light bulb. So your current's going to flow from the battery through the switch. It flows up through the light bulb. And because the switch is closed, we have a completed circuit. The light bulb lights, and the current flows back to the battery and just keeps flowing in that same circuit. That's because it is closed. As a closed circuit, the switch is closed. Once you open up that switch, the current tries to flow and it has no place to go. And since it cannot complete this circuit, complete this path, the light bulb doesn't light, there is no current flow. Okay? So a way to maybe better understand some of these concepts of voltage and current flow and so on is to think of an analogy here of how water flows. The flow of water through a hose is similar to it can demonstrate the characteristics of electricity and how it flows through a circuit. In a water hose, the water is like the electrons that flow through an electric circuit. Friction, which prevents the water from flowing freely in a hose, is like resistance in an electric circuit. And pressure, the water pressure that causes the water to flow, is like voltage in an electric circuit. So that's one way of visualizing it. And you can see here in this drawing here, you'll see that we're measuring the pressure again across a load, in this case, the pump, whereas we measure the flow in series. Here it's in parallel. The meter is in parallel with the system, whereas here for measuring flow, it's in series. Similarly, over here, we measure voltage in parallel across something in the circuit, whereas current, we measure in line or in series. Okay. Continuing with this analogy a little bit, you can think about you have a hose connected up to a faucet, and the nozzle is closed, but the faucet is open. Well, there's water in the hose, and there's pressure that would force the water out. But as long as that nozzle is closed, nothing happens. Similarly, with an electrical system, where you have an example here of a lamp plugged into an outlet, it's plugged into the outlet. There's electric potential, there's voltage at that outlet, but the switch is off, so nothing is flowing. So there is no current flow. With the hose, once you open up the nozzle, then the water can flow and it can move through the hose. Similarly, with a lamp, once you turn the switch on, then there's a completed path for the electricity to flow, and it does. Okay. And electricity flows through what we refer to as conductors. There's conductors and insulators. In a conductor, electric current can flow freely, and in an inductor, or in an insulator, it cannot. Most metals are good electrical conductors, and most non-metals aren't, as a general rule. Metals are also generally good heat conductors, and non-metals generally aren't. So if you look at this picture here, it shows a cross-section of copper wire. So it's the electrons on the skin of that wire that are moving. And basically the electrons create a chain reaction. Good conductors have a weak hold on what are called their valence electrons, their outer electrons. They can break loose and move to another atom. And that creates current flow when they do that. And good conductors have those free valence electrons. Insulators do not. So your good conductors are things like copper, silver, gold, aluminum, platinum, steel, the metals, right? Insulators are things like glass, wood, rubber, even air is a good conductor, or insulator, I mean. Interestingly, pure water is an insulator, but very difficult to have pure water. Usually there's some sort of contamination in the water, and salt water specifically is actually a conductor. And so are we, because most of our cells are made up mostly of salt water, essentially. So we're a good conductor, which is not a good thing when you're playing with electricity. Okay, so looking again here at parallel versus series circuits, you can see we've got loads in parallel up here at the top. When you have a parallel circuit, the current has more than one path to follow. So the current splits up, if you will. Loads in parallel will have the same voltage across each load, but the current flow will be different because the current splits up, essentially. And depending on how much resistance will determine how much the current flows through each of those. In a series circuit, the items are in single path. There's only one path, so the current is a constant throughout the circuit, but the voltage will be different across each load. There'll be a different voltage drop across each load, but the current will be the same throughout. So that's another difference between a parallel circuit and a series circuit. So the way to kind of think about this and remember, the old Christmas tree lights that we always love to mess with, right? So here's a series circuit. So we can see here we have a battery, and we're going to have the current's going to flow through one light bulb, through the next light bulb, through the next light bulb, and back to the battery, which is all great until one of those light bulbs burns out. If one bulb burns out, suddenly the path is interrupted because there's only one path for the current to follow, which is why you have that problem with some of the cheaper, older Christmas lights. One bulb goes out, they all go out, right? Not true with a parallel circuit. With a parallel circuit, you've got the current and it branches off, in this case, into 3 different branches, and then goes through the 3 different loads and returns back to its source. If one of these bulbs burns out, there's still 2 other paths for the current to flow through, so those bulbs remain lit. So that's difference in the characteristics of series and parallel circuits. All right, so now let's talk briefly about DC current and AC current, direct current and alternating current. Direct current flows in one direction. For example, those illustrations we've shown here with a battery hooked up to light bulbs, that's direct current, flows in one direction. Alternating current flows back and forth in both directions. And you can see on the right there, it shows it's forming a sine wave. It goes from 0 up to the maximum, then it goes back down to 0 and down to a minimum and back up to 0. Alternating current, which is what you have in your electrical outlets at home, alternating current. So getting back to that analogy of water flowing, you can think about direct current like a waterfall, right? The water has only one direction it can flow in. It flows in a single direction, and that's it. And that would be the example here with a pump, pumping water through a pipe in a circuit, in a circle like that. Alternating current is basically in waves, the sinusoidal wave. You can think about it like the waves coming into a beach. It comes in and it goes out. It comes in and it goes out. And you can see this illustration here of the water with a pump that pumps in both directions. When you pull up on the plunger, the water goes in one direction. When you push down, it goes in the other. So as you lift up and down, you get an alternating flow, just like alternating current would alternate. Another type of alternating current is the current produced by RF radio frequency waves. The green represents the electrical portion of an RF signal hitting an antenna, and it induces current in that antenna, and that becomes an alternating current that gets induced. So the last of our terms here for this section, capacitance. It's the ability to store energy in an electric field. That's called capacitance, and it's measured in a unit called a farad. Inductance is the ability to store energy in a magnetic field, and that unit of measurement is called a Henry. We measure inductance in henries and capacitance in farads. Impedance is opposition to current flow in an AC circuit. Remember, we talked about resistance in a DC circuit as resistance to the opposition to the current flow in a DC circuit. Here we're talking about opposition to current flow in an AC circuit. They have a different name for it. They call it impedance, but essentially they're both types of resistance, and both cases the unit of measure is the ohm. So resistance and impedance are both measured in ohms. All right, so let's take a look at our question pool here. Why are metals generally good conductors of electricity? Remember, we said that their valence electrons freely move from atom to atom, so they have many free electrons. That makes them a good conductor. Which of the following is a good electrical insulator, not a conductor? Remember, we said that good conductors are metals. The one thing there that's not a metal is glass, and glass is a good insulator. Which type of circuit is DC current the same? The current is the same through all components. Remember, they're all in a line. They only have one path to flow through, so it's going to be in series. You will have the same current through all the components in that circuit because there's only one path to follow. In which type of circuit is voltage the same across all components? Well, that's the opposite, a parallel circuit. So remember, there's different paths for the current to follow, so the current will not be the same across each component, but the voltage will. Which of the following describes alternating current? Okay, the answer is C. It alternates between positive and negative directions. The other first two answers say it's positive or negative and zero. And no, it's between positive and negative directions. It's a complete cycle. What describes the number of times per second that an alternating current makes a complete cycle? Okay, the number of times. So how many times is it doing? How frequently does it happen? The frequency. High frequency, a lot of cycles per second. Low frequency, fewer ones. What type of current flow is opposed by resistance? Direct current, alternating current, or RF current? Actually, all of these are correct, because remember we said that impedance is another term for a type of resistance in alternating current, and RF current was the same concept as alternating current. So yeah, so they're all actually correct choices. It would be easy to get fooled with this question, but it's all of the above. What describes the ability to store energy in an electric field? That was one of those terms in the last slide we were defining. That is capacitance. This goes with an electric field. And the unit of capacitance is the farad. Remember, ohms is resistance, volts is voltage, and a Henry is inductance. What describes the ability to store energy in a magnetic field? Again, that same slide, the other one was the magnetic field, and that was inductance. So inductance is magnetic field, capacitance is electric field. And the unit of inductance, which I just mentioned on the last slide, is the Henry. The Henry. Okay. Any questions on that before we move into the next section? Okay. Ohm's law. This is important. Ohm's law is the relationship between voltage, current, and resistance. And we've already defined what those terms are. And you see this circle over here to the right. E is voltage, I is current, R is resistance. And this is a visual aid that you can use. So the E is above the I and the R. The I and the R are next to each other. That means they get multiplied together. The E over the R, if you divide E into R, you get I. I'll show you all that in a minute. But this is a relationship. We're going to get into this a little further. There will be a number of questions that relate to Ohm's law on your exams, in the exam pool. Okay. Another definition here, we want to talk about decibels. It's a unit for expressing the ratio between two physical quantities. Example we're going to use is power. It is a logarithmic relationship. A logarithm simply the reciprocal of a power of 10 function. So for example, shows here log x equals y means that x is equal to 10 to the y power. Okay. So what does that mean for us? Well, what we need to know is pretty simple. You can see that this curve is a logarithmic curve. And what we care about for the exam purposes is three numbers, 3, 6, and 10. A 3, this is decibels on the bottom, and power multiplier on the y-axis here. So 3 dB is twice the power. So 3 dB is a doubling of the power. 6 dB is 4 times, quadrupling of the power. So if we have a 3 dB increase in something, it's doubled. If you have a 6 dB increase in something, it's quadrupled. If you have a 10 dB in something, it's 10 times as big. Okay? And those are the only numbers you will see in the exam pool. That's the only ones you need to worry about. Okay, so here's an example. You've got, let's call it 1 watt here in the middle here where it says 0 dB. There's no change in anything. If I go plus 3 dB, I've doubled it. I now have 2 watts. If I go to 6 dB increase, I quadruple it. It's 4 watts. If I have a 10 dB increase, it's 10 watts. If it's a reduction, if I have a minus 3 dB, a 3 dB reduction, it's 1/2 of what I started with. If it's a 6 dB reduction, it's 1/4 of the original. And finally, if it's a minus 10 dB, it will be 1/10 of the original power. And if you don't understand decibels, that's okay. Just memorize that 3 dB is a doubling or halving. 6 dB is 4 times or a fourth, and 10 dB is plus or minus 10 times, either 10 times or 1/10. Okay. Watt's law. We talked about Ohm's law, and I'm going to talk about Watt's law. I have a picture of a pi there because it's potential, current, power, electromotive force is E, current flow is I, power is P. So you have P over I and E, or pi, okay? And the formula for Watt's law is P equals I times E. And we're going to see some examples of this. Okay, so I would suggest you memorize these 2 circles, and when you have your scratch paper in your exam, if you're unsure of yourself, once your exam starts on your clean sheet of scratch paper, you can write down, draw those 2 circles and put the letters in them so that you'll have them as a reference to figure out these questions if you need it. It's one way to do it. Okay, so if you want to solve for something, you cover that letter with your finger, and then it will show you how you solve for that other value. For example, if I want to find the voltage for Ohm's law, I put my thumb over that, and then what's left as I see is I times R. So if I want to find voltage, I know it's I times R. let's say I want to find current. I put my thumb over that, and what I see is E over an R. That means E divided by R. Similarly, if I want to find resistance, I cover the R and I see E over I. I know that I need to divide the voltage by the current. Same thing with the Watt's law circle. If I want to find P or power, I cover that up with my thumb and I see an I and an E next to each other. They're multiplied together, so current times voltage. If I want to find the current, I cover that with my thumb, and what's left is P over E. I divide the watts by the volts to get the current. And finally, if I want to find the voltage, I put my thumb over that and I see that I have power over current, so I divide the watts by the amps. That's why we show this. All those combinations, you could actually have a chart like on the right that tells you what each of those are. Which one would you rather memorize, the one on the left or the one on the right? I think that's kind of a no-brainer. It's the one on the left that you want to do. So let's apply these to the question pool. What formula is used to calculate current in a circuit? So here's our choices. We're not going to go through each of the choices. Let's see how we actually solve this. So what we want to do is we want to look at that circle, the Ohm's law circle. So we want to find I, we find the current. We're going to put our thumb over the I. We see that it's E over R. Okay. What formula is used to calculate voltage in a circuit? So we're going to do the same thing. This time you put your thumb over the E, you see it's I times R. What formula is used to calculate resistance in a circuit? Same thing. Thumb over the R, E over I, that's the answer. What is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? So now we're going to actually put numbers with this. So here we want the resistance. We put our thumb over the R. We know that the volts is E is 90 volts on the top, and we know that I is 3 amps on the bottom. So it's 90 divided by 3, or 30 amps, or 30 ohms. That's the correct answer, 30 ohms. What is the resistance in a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps? Going to do the same thing. We put our thumb over the R. We see we have 12 volts over 1.5, or 8 ohms. What is the resistance of a circuit that draws 4 amps from a 12-volt source? Same thing. Put R, thumb over the R, 12 over 4, 3 ohms. What is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? This time, we're going to put our thumb over the amps. We've got volts over ohms divided out, 1.5 amps. What is the current through a 100 ohm resistor connected across 200 volts? Again, thumb over the current, voltage divided by resistance, 2 amps. There's a lot of these questions in the pool, but they're all solved the same way. What is the current through a 24 ohm resistor connected across 240 volts? Again, 240 over 24, 10 amps. What is the voltage across a 2 ohm resistor if a current of 0.5 amps flows through it? This time we got our thumb on the E. We got 2 times 0.5, or 1 volt. What is the voltage across a 10 ohm resistor with a current of 1 amp flows through it? Same thing. Thumb over the E, 10 times 1, 10 volts. What is the voltage across a 10 ohm resistor with a current of 2 amps? Same thing, different numbers, 10 times 2, 20 volts. Okay. Now, shift into some different concepts here. Which decibel value most closely represents a power increase from 5 watts to 10 watts? Well, an increase from 5 watts to 10 watts is a doubling of the power, right? And remember, 3 dB is a doubling. 6 dB is 4 times, 10 dB is 10 times. So it doubled, so it's 3 dB. Which decibel value most closely represents a power decrease from 12 watts to 3 watts? Well, half of 12 watts would be 6, and half of that would be 3. So it's a 1/4, and it's a reduction. So it would be a minus 6 dB. So you can look at it as 12, half of 12 was 6. That's a minus 3 dB loss. 6 divided by 2 gets you to 3 watts. That's another minus 3 dB. So you got 2 minus 3 dBs, or 6 dB is your loss in that case. Which decibel value represents a power increase from 20 watts to 200 watts? Well, that's 10 times as big, right? And it's a positive, so we know that that would be 10 dB. Okay, so applying that pie chart, if you will, the pie circle, what is the formula used to calculate electrical power in a DC circuit? Okay, again, PIE, but it is P equals I times E. How much power is delivered by a voltage of 13.8 volts DC and a current of 10 amps? We're going to use that pi circle. What are we looking for? We're looking for power on the top of that circle. So we're going to cover up the P. We know that the current is 10 amps, the voltage is 13.8. They multiply together to give you 138 watts. How much power is delivered by a voltage of 12 volts DC and a current of 2.5 amps? Going to do the exact same thing. We're solving for P again. We're going to put our thumb over that P, 2.5 amps times 12 volts. Okay, 30 watts. How much current is required to deliver 120 watts at a voltage of 12 volts DC? Again, this time we're solving for current. We know that there's a power is 120 watts and the voltage is 12 volts. We cover up the I. We know that it's going to be 120 divided by 12, or 10 amps. Okay, any questions on that before we move on to our last bit here? Okay. What does the abbreviation RF mean? Remember, we talked about that. RF is radio frequency. It's not a resonant frequency or a real frequency or a reflective force. It is radio frequency signals of all types. It's a general term for radio frequency signals. What is the abbreviation for megahertz? We've already looked at this before, right? It's MHz, but it's capital M, capital H, little z. Okay. What is the abbreviation for kilohertz? Kilohertz. Okay, so we have hertz, capital H, little z, and we put a K in front of it. But remember, with kilohertz, it's a lowercase k. With megahertz, it's an uppercase M. So this is little k, big H, little z, kilohertz. What is impedance? Okay, remember we said it was the opposition to AC current flow. It's the AC current equivalent of resistance in a DC circuit. It's opposition to the current flow. And the unit of impedance, just like resistance, the unit is ohm. It's the ohm. All right, and that's the question pool for today's session. Any questions on anything? I know it's a lot of math, but it's simple math, and you can have a calculator if you need it for the exam.